Hi everyone. Today we will talk about One-Byte-Overflow. It is a story of how a very small leak caused sinking of a great ship. We'll first talk about how One-Byte-Overflow happened in a real-life example in Google Chrome OS, and then we will talk about how it affects the heap and some takeaways we learned from it. In Google Chrome OS, there is a CS4 that grants root access. The flaw existed from 2003 to 2016 for 13 years. And the people who finally discovered get a $100,000 bounty. The security breach happens on a function called iris query. This is a string processing function that takes in a string of names separated by dots, and then it will remove the backslashes and remove the separating dots and then replace it with length of names. And then it will append the DNS number after the string and return it. This is the function. And this function sounds so simple that it's like a function that we can wrote when we just started learning programming. However, even so simple, there's a security breach. At first, in the function, the programmer calculates the length of the processed string here, because and here they ignored the backslashes, and because at the end of the processed string we need to add the DNS number, and since the names are separated by dots, sometimes at the end of the input string there is an ending dot, sometimes there isn't an ending dot. So the programmer thinks that if there is an ending dot, they will replace the ending dot with the DNS number. If there's not an ending dot, the processed string should have length +1 to append the DNS after the string. However, in the case that if the ending dot follows after a backslash, we can find that in this situation, the name doesn't change. However, the length is one byte short. So we can see that if we give the input as a name A, name B, it will return a string of 1A, 1B, and the DNS number 0. The supposed length is 5, the actual length is 5. We put A dot B dot, it still returns the same string. However, if we give the input A dot B slash dot, it will return the string 1A, 1B dot 0. And the actual length of the return string, process string, is 6. However, the program thinks that the supposed length is 5 and give a malloc memory of 5.
So after learning how the one-byte overflow is implemented in the real-world exploitation, you might ask, is 1 byte enough? Well, before understanding the attack, we should understand the basic structure of malloc chunk, and then we will get into how the shrinking free chunks attack actually happened, or the forgotten chunk. The image on the right side is the structure of the malloc chunk, and as you can see, it contains previous size and size. But the previous size is only activated if the previous chunk is free. For example, if we see this header of C, we'll see that it has a previous size because the previous chunk B is free. But for B, it will only contain the variable size because the previous chunk A is occupied. Therefore, the header of B will start with the size, but the header of C will start with the previous size and followed by its size. Now let's take a look how this attack works. So at first we'll make 3 malloc, chunk A, chunk B, and chunk C, and the rest of it will be free. Then we will free chunk B, which will update the header of C. More precisely, it will update the previous size variable, and it will set it equal to the size of B, which is 208 in hex value. And then we'll input a string into A, which will cause overflow into B 1 byte exactly. And this 1 byte will affect the least significant bytes in the size variable. So the size inside the header will be truncated to 200 from 208. However, this will not affect the previous size variable in C because this only poisons B, and C will still think that, oh, its previous size is 208, and B will think itself only 200. So there is the asymmetric information. And if we make malloc B1 and B2, the B will think, oh, B will use its size, 200, and call some address here. This will be 200 from this address. And it will say, oh, our chunk is shrinking. You should update your previous size. However, this is not chunk C's address. So the chunk C's previous size will still not be updated. It will still think that it is 208 instead of this part. And after that, we will free B1 and C. So when we're freeing C, the C will automatically coalesce with the previous size, the address plus its previous size. So if we use that previous size 208 and this address, it will trace back to here, which is the original address of B. And it will ask B1 that, oh, are you free? And B1 will say, yes, I am free. And then they will coalesce together, not realizing that they are actually not next to each other. And remember, B2 is still in use. So everything that is stored in B2 will be in danger. If we make one final big chunk request using malloc, it will be taking place here rather than here, which is the scenario where the coalesce happened here and nothing is poisoned. If it takes place here and we store something really big inside the big chunk, the memory in B2 will be overridden. Therefore, the memory in B2 will also be poisoned, and thus conclude the shrinking-free chunks attack. So now let's look at some demo. First, we'll make 3 allocations, A, B, and C, and here are the address and the size of them. If we free B, then our free chunks candidate will be B and also the big chunk over here. And as you can see, the size here matches the size of B. Let's enter something, say I love CS. So this does not cause any overflow, so the size of B doesn't change, and also same with the precise in C. Now let's enter some secret into B2. I love kitty. So now we have 2 strings. The string A is I love CS, and string B2 is I love kitty. And if we free B1 and free C, this will result in this stage 6, where one free chunk is B1, and one free chunk is actually the entire red block, as you can see here. So if we malloc the big chunk will be taking place in the second free chunk. And thus, if we enter something outrageous here, it will not overwrite anything in B2. As you can see, the address of the big chunk is after B2, therefore it will not overwrite it. Here's a demo with the overflow. So in A, we'll input something like this, and this will cause an overflow. As you can see, the size of B, the free B, is truncated from 290 to 230. This is due to this 1 byte 0 here is actually has a hex value of 30, and that's why the 90 here is changed into 30. And the precise in C is still the original size of B. So if we enter the same secret, here's our string A and B2. And if we malloc the big chunk here, the address of the big chunk now is ahead of the B2, because now we have reached the stage 7 where the 2 malloc overlap each other. So now if we still enter the outrageous text, the string B2 will be overwritten by the big chunk. And now my secret is poisoned and my day is ruined. So here are the takeaways. In our demo, the normal malloc mechanism is that when we're freeing C, it will use its address and its previous size to find the previous block and to check if that block is still free. If it's free, they will coalesce with each other. But we can add one more step to make this process safer, is to check it bidirectionally. So after we check in the B1, we'll also use the size in B1 to check if the C is indeed the next block. And the second lesson is that the 1-byte overflow is dangerous. It might seem very limited, but with the right amount of skills and luck, it can still do some serious harm. Thank you for listening.